All right. Well, today is a continuation of what I started last month, where it was really looking at collecting and doing a first pass at field data and field data analysis. But there's a whole other class of data that deals with factory equipment, or more generally with renewal data, with repairable systems. And that data tends to occur in a little different way, and the analysis is a little bit different. And so we'll explore a pretty simple way to get started with that, and just mention a couple of more advanced techniques for doing that. And it's it's something that I've learned kind of the hard way. I traditionally always used the same approach for all this, for the different kinds of data, but I found that the analysis is significantly improved and also easier to understand with this cumulative plotting idea that we'll talk about. So one of the reasons we look at data is to adjust our maintenance strategy. Is simple things like, are we experiencing a wear out in this fleet of, say, motors or valves, and do we need to be more proactive in repairing those? Or are the repairs occurring primarily at the installation, and we need to improve either the screening or the installation practices or some other aspect to reduce those early failures? But being able to tell the difference then allows us to adjust our strategy appropriately to improve our overall plant's maintenance posture. The other thing is to prioritize. Some organizations and some factories may have thousands, if not tens of thousands, of assets. And so by routinely collecting data and focusing on the ability to improve the things that are most important to your plant, the better. And so, Jason, I just saw your note on an echo in the voice. Hopefully, it's not just my morning voice, but is it bearable, or should I try resetting or doing something like that? I've got to do a quick sound. It sounds good there. Sounds good. So sorry about that, Jason. Sure. One idea, Jason, is to sign out and sign back in. Sometimes that takes care of it, and it looks like he just did that. So hopefully that takes care of the echo. All right. Thanks, everybody. So anyway, one of the reasons we look at our repair histories and data is to move out of the anecdotal evidence of, saying, oh, geez, I just repaired that last week. It must be something wrong. Whereas if you have a complicated system and lots of different repair activities going on, that may not always become obvious what are the top priorities that you need to focus on. It sounds like my neighbor's dogs are getting excited about something, and just in time for my little robot dog here. But we also use data analysis to detect things in our detection process, in our preventative maintenance program, in our equipment's aging and its behavior. And ideally, we can detect issues before they become catastrophic failures. And so a little bit of data analysis and some extra work from that data analysis can really help us to solve problems in many cases before they occur. So it's one of the reasons, a couple of different reasons why we do this stuff. And so I want to ask a question in the group and get the chat window going more than just saying hi and sound checks. Is do you have repairable system data or asset management kinds of data? And what kinds of systems are you dealing with? Yeah, repair data is pretty general. The idea, though, is that if you have a system, say like your car, if every time you repair it, it might be something different and occasionally the same kind of activities, uh, and you're looking at the overall system, then that's what I'm talking about. It's something that is, well, when did it get repaired? When was my system down? And things like pumps, motors, instrumentations, CMMS systems are a common place where we track work orders and planning work and stocks and storerooms and things, but also we capture the date of the failure and how long it was down. And if we're doing really well, then we also capture root causes and improvement activities. And cause codes, I think you're right, John, there's all kinds of things that get captured in there. What parts fail? Yeah. I've not always been really good at tracking my cars and the types of repairs that need to be done on it. I know when I was in high school, I had a late model car that was pretty old, and my dad kept track of it because he was getting these bills for a fuel pump, a water pump, a radiator, an exhaust system. And at some point, he said, you know, we've put more repairs into the car than it's worth. So he saw this increasing rate of failures, which I suspect he thought had something to do with the way I drove and maintained the car. But either way, I ended up selling that car and getting a different one that had a much better repair history once we started using it. But yeah, there's all kinds of factories and plants and equipment that we deal with that we need to have it running. And when it goes down, whether it's unscheduled maintenance or as a unscheduled repair, we tend to keep track of that kind of data. And so the real question is then what do you do with it, right? How do you evaluate that information? And there's, especially for I see a number of folks are talking about uh, uh, coding systems to classify whether it's a pump or it's a motor or different types of assets that it belongs to within the organization. That all helps us to sort, to filter out our data to look at particular elements of our assets at one time. But let's say you've got a stack of data, right? And I'm going to use a couple of examples here. And Brian, I'm going to come back to that MTBF one. I was waiting for somebody to bring that up. As many of you know, I'm not a huge fan of MTBF and actively am working to get rid of it. And I'll illustrate simply why, one of the reasons why I don't like using it. But let's look at an example. I created 3 sets of data, just hypothetical pieces of equipment, and you might pull data from a CMMS, or you might have some handwritten records, or you might be keeping track yourself. And let's say I'm looking at this 3 different machines in my factory, and I've run them for about 1,000 hours of active running. And this particular machine has had 10 repairs executed, 10 failures that a technician had to go out and do a little diagnosis work and repaired something or adjusted something, but got the machine back up and running in pretty quick order. And so we end up with this a set of data. And the way this data is collected is that we started at time 0, and at 112 hours, we had our first down event, and it got repaired. And then 198 hours of operating time, total operating time, since it got installed and turned on, or we started tracking the data, I get another failure at 198 hours. And then it runs for a little over 100 hours, and it fails again at 301 hours and if it's lifetime, and so on. And so I just have 2 columns of the time markers of its age, basically, or operating runtime of when it went down. And so very, very simple data. But what do you notice about this information? What do you see in this table of numbers? And so appreciate that, Brian, that you're not. Well, hopefully I'll give you just another piece of info to talk about it. Yeah, and Bill, I agree. There's not a whole lot. It's a set of numbers. And if you squint at it really hard and maybe look at it a number of different ways, you might pick out something about this data. Yeah, and it sequenced roughly 100 hours between failures, exactly. And it was the way I just created it. Uh, but it's not exactly every 100 hours, and real data is often much more messy than this, but this is intended to be pretty stable. So machine 2, a little bit different. What do you see in this one? Yeah, lots of eights. There's three of them in the 800-hour range, and so it's tending to bunch up in the end. Yeah, and Jay, I was trying to represent a data set that was showing that it was getting repaired more often as it got older. Now, this would be an example of that car I had in high school, right? And so it takes a little bit of mental work and some quick calculations, and if you're very fast, you just plot this data and you probably see these things. And then the third example is just the opposite. There's more failures early in the 100 and 200-hour frame, and then it spaces out. Right. Well, as you can see, just looking at the so Bill, I'm going to one way to look at this is you can look at 10 different machines that each have a failure, and you're looking at a system, say a line that has 10 machines. That's one way to do it. I tend to focus this data on a system, whether it's the line or, say, a bottling piece of equipment or a packaging piece of equipment or like a vehicle at one time. I'll mention a way that this gets extended to multiple machines with multiple failures on each machine and how you can use that analysis. If you have 10 machines and each has only failed once, it may be appropriate to use a Weibull analysis looking at time to first failures. It's the renewal data is usually what is characterized by it's the same system, like a vehicle or a factory piece of equipment, that fails multiple times, often for different things. So it might be a bearing that's replaced, and the next time it's an alignment adjustment that occurs. Another time it's down because of a jam, or another time it's down for a motor being replaced. It could be multiple different specific repairs that occur, but it's on one machine that you're interested in. Yeah, and you're exactly right, Robbie, is the data sets are set up to show three different patterns. But the data sets themselves really doesn't often tell us the whole story or reveal what's really going on. And so now, Brian, you mentioned MTBF. And so the typical way to calculate MTBF is to tally up the operating hours. And here I'm using artificial data, and each machine is run for 1,000 hours, and each of them has had 10 failures. So I can calculate the MTBF for each machine. It's pretty simple. I actually contrived the example so that I could do this in my head even. But I get 100-hour MTBF for machine 1, right? And for machine 2, and for machine 3. And by simplifying to this average, essentially, this inverse of an average failure rate, I don't even have as much information as just looking at the data set of 10 numbers in each case. Right? If I was to give you only the MTBF values, we would not be able to conclude that machine 2 is showing wear out, machine 3 is showing early life failures. So MTBF is a step backwards from just the raw data, right? So it's a simple example, but it's one of the many, many ways that MTBF just leads to poor decisions. So if I was only given this data and summarized it as MTBF or something similar, mean times between unscheduled removal in the aerospace industry, and there's MT fill in the blank for different industries and different circumstances. But how would you approach your maintenance strategy for these three machines given just MTBF? Yeah, right? Not a lot we can do about that, right? We treat them all the same. We typically just wait for failure and go run out there and be a good fire department. Yeah, and John, you're exactly right. And I agree with you, Brian, is that, yeah, use it under protest. We are battling on the nomtbf.com site is a series of issues like this and articles like this and stories and successes. We're actually making some progress of convincing people like you, Brian, to make a stand and help educate the rest of the industry that this is really going backwards. All right. Well, when I was preparing this data set, I wanted to make just a simple plot, just a one-dimensional plot. And it ended up taking me a little while to figure out how to do it so it would look the way I wanted it to look, just creating a computer plot of it. But so the thought was, well, once I sorted it out, I took my first set of data, that machine one, and as you saw in the data set, it's just roughly evenly spaced, right? And so it's easier to see right here. I have the exact same data set. It's just spaced out over a timeline, essentially, and the little dots represent when the failures occur. And it's great. And so, Alfredo, I just saw your hand going up there. Thank you. And I'm going to, let's see, you have a question. Assume beta in a Weibull formula. Yeah, and one of the thoughts is, and I see the notes, John, you're talking about, there's plenty of other questions going on here and what we need to evaluate. So there's more to it than just the data, but oftentimes a simple plot can help us then to ask better questions from our system. Where do we need to do the failure analysis? What do we need to evaluate next time we go out and look at this equipment? So if, for example, in this machine one with the roughly 100 hours of operating between failures, what would you go do? What would you change in your approach? And I'm looking at failure modes and effects analysis or a risk analysis, or maybe collect some more data. Is there something vibrating loose that manifests a failure after 100 hours? And so maybe what we're fixing are symptoms, not necessarily the cause, but what kind of behavior would cause this pattern of failures, which is a whole completely different question than just running out and fixing problems. Yeah, looking at what happened. Yeah, John, I agree. There's a lot of things about human factors, especially about complex equipment. But what about it? Is the maintenance not effective, or is it effective? Is the preventative inspections and evaluations, are we missing something in those things? So it's, if this was our top priority and biggest money loser and affected our uptime the most, we would certainly spend more time working on this equipment. And it's all conjecture at this point, but what the idea is that let's let our data help us ask better questions. Yeah, and Carol, I agree. It's are these 10 different elements on the equipment that failed, or is it only 2 or 3 elements? Say maybe 2 or 3 motors that are consistently having the problems, and so is there more depth to what we need to look at? But I'm going to show that. I'm listening to a huge truck coming up the hill outside our house, so hopefully that's not too bad in the background. I must have a pretty big load on it. So anyway, let's look at machine 2. Should be immediately obvious that the failures are bunched later. And if I was an operations manager and looking at this, I would be saying, hey, what's going on? Are we going to make it to 1,000 hours? You know, are we going to get a failure per day here pretty soon? Is it wearing out? Is there something else going on that's creating this a collection of failures near the end? And while we saw that in the raw data, this very simple plot pulls it out really fast. And it's just a dot plot. And I think Excel can do it. I wanted a nice clean graphic, so I used a different method. In Machine 3, it's just the opposite, right? We see the bulk up front, and if I saw the wear out or this early failure pattern, I would change where I ask questions, right? I'd be here on Machine 3, I'd be looking at installation and startup issues, and were these adjustments and refinements that helped it to get better over time, whereas the wear out ones are, is there wear or corrosion, is there age-related issues that are dealing with it, or maybe my maintenance practices are actually making it worse every time I touch it. And so it's a different set of questions for each of these patterns. That's kind of the idea, is let that data show you what's going on. Let it tell its story of what's happening. All right, so let's take a look at this a little bit closer, and then I've also got some examples that I wanted to share with you and see what you thought about some real data that I've seen. So one of the ways to evaluate these, a little bit different than raw data or a dot plot, is a cumulative plot, and we'll go into that. And so is everybody here, or is anybody, I'm not sure how to answer it. Let me ask it this way. Is anybody not familiar with a cumulative plot? Yeah. Ryan, yep, reviewing the PMs and then looking at the recurrence of failures related to what you've been trying to solve. If you're spacing them further apart, your PMs are working. If it's occurring more frequently, maybe you're causing problems. So Brian uses cumulative plots, good. A couple of people use them, all right. Yeah, and it's one of the things I ran into some years ago in the literature by Wayne Nelson and by Dave Trindade have both written about it, and a next step on it called a mean cumulative function. Yeah, and it's a pretty eye-opening is probably the right word for it. Let's take a look at creating one for the folks that maybe are not familiar with it. So essentially what I've got is just time, and that could be in hours or days or whatever time unit is appropriate for the system you're evaluating. It might be miles driven or hours of operating time or whatever is appropriate. And then the vertical axis is just the count of the repairs or of the downing events, for example. Right? So it looks like we got a few people that are using it. So I'm not seeing everybody chime in there. So I'm going to explain it very quickly here. So it's a very basic plot, the number of repairs versus time. And so the first data point, let me get my little drawing tool here, hopefully it works. Let's say I have run for some number of hours, say 100 hours, I'll just use a point there, and my axis here for my first failure point is just going to be a point right here. It's all it is I basically am doing a staircase kind of plot where it goes no failures out to this point in time. I get a report of a failure, we go out and fix it, and then I'm off and running again. And I keep going until we get a second failure. And if I do this right, oops, I have to take that off. There we go. And the idea is, still getting used to my drawing tool, even though I've been using it now for 2 years. So I get a point, and then some hours later I get another point, and so on. And so each time I get a failure, I increment my vertical axis by 1. So it's just a cumulative count of failures and then where they occur over time. So pretty basic, right? And it's completely non-parametric. I'm not making any assumptions at all other than the reported time of the failure or the downing event or the repair action is reasonably close to when it actually occurred. And that's going to be an issue for everybody, is how accurate is your data. If you've got sensor logs and it's fairly computerized, it might be fairly accurate. Then it tends to add noise of things that are false failures or just way too much data. Whatever way you gather it, though, it's basically you're just looking for when did the failure happen. And then you can arbitrarily pick, say, the start of the year, the start of the month, whatever time span you're interested in, and set that as 0, and start counting failures and when they occur. So it's essentially a very simple plot, very similar to that dot plot, but it has this count, this cumulative piece of information to it. So let's see what they look like when we plot it in our 3 sets of data. So machine 1, as you could see in the raw data, which you could not see in the MTBF, but might assume, is that it had a fairly consistent pattern. And the repairs I'm doing are not fundamentally changing the chance of failure going forward. It seems like a fairly consistent pattern of failures. But it becomes very obvious here because it's easier to see a line on a curve when the data is at about a 45-degree angle. There's, I'm trying to remember his name, is Tukey and others have done a ton of work on plotting and how people interpret plots. And one of the concepts they came up with is that if you're going to adjust the scales of your plot, is do it such that the data is at about a 45-degree angle. It enhances the ability for a human to interpret it. So it was one of those things I picked up some years ago, and I thought, oh, that makes sense. Because as you know, if I wanted to show that we don't have a very much of a problem, I would compress the vertical axis, and it would look like a fairly flat line, and it would misrepresent the data. The interpretation would be, let's see if I get my drawing tool up again, right? If I have a line that looks like this, only because I compressed the scale, maybe made the vertical axis 0 to 100, it would look like, oh, it's a fairly flat line, it's no big deal. Where if I changed the scale such that it was much shorter, I would have an almost vertical scale or line on it. And we would inherently, subconsciously to a large degree, interpret that as being a significant problem. So as you're plotting your data, allow your viewer, the person evaluating that plot, to make their own judgment of interpreting the duration to the number of failures. And 45 degrees is typically a good spot to shoot for as you set up your scales. So just a side note there. Yeah, you can make things work. I think it's part of that How to Lie with Statistics book is mess up your scales so that you can get the message you want across. Where let the data talk. Let people interpret the data for what it really is. And so keeping it as clean as possible and let it tell the story. One concept of that is have your data show about a 45-degree angle as best you can. So here I've got a curve though. This is the data set we said had some wear out behavior into it. It was bunching failures near the end. And one of the things we can see right away from this is more than just that we have lots of 800s. We had, I think, 3 of failures in the 800 time frame. Is it shows a little bit of a curve, right? And it's this, I always get concave and convex wrong, but it's increasing with time. The slope is increasing with time. Now look at it carefully. The distance between 800 and what is this, 825, I've got maybe 1.5, 2 failures in there. Whereas if I look at the same interval, say between 200 and 225, there's nothing. And the chance of a failure occurring here is a little more than 1 overall, but it's a small chance of it occurring, where here I'm going to get a couple failures in the upper part of this curve. So depending on how old the equipment is, I have a different chance of failure. So the more it runs, the more likely it is to fail. And if it's increasing steeply like this, well, there's something else going on that we need to ask better questions about and see it. But it's the slope, this deviation from a straight line, that tells that story. And we don't need to do a lot of mental math and looking at a table of numbers. The simple plot just jumps it out at us, and that's the idea. Now, of course, the second or the third machine has got the opposite kind of pattern, right? And you're right, Bill, is that, and Brian, that the visualization skills are important, right? And here I've got artificial data, so my scales are nearly identical. I think it's from 0 to 10 and 0 to 1,000 days. So it was pretty convenient. But the idea was to show that you can see these arcs that occur in the data that then tell completely different stories than just squinting at a table of numbers. And it's pretty rare that we get just 10 data points. In some factories, you may have thousands of failure incidents that you're needing to plot and evaluate. Or you may be looking over longer time frames where you have a bunch of data also. So here, it's just the opposite behavior. You can see that the data points are spacing out as the equipment gets older, right? So there's just a longer distance, like we saw in the dot plot, than it is earlier in its life. But it's even easier to see because it's curving over, it's bending over. And this, and again, I think it's concave, if I remember right, curve. I think my geometry class teacher is going to be rolling her eyes at me. I probably missed it on a test too. It's probably, I still didn't quite learn it. Looks like a cave. Oh, okay. I probably still won't get that right. I think I have a mental block there. Well, anyway, thanks, Bill. Yeah. But the idea here is that if it curls over like this and goes concave, there's some reason for that, right? There's usually some phenomena that's occurring. Maybe we implemented a change in our maintenance practices at, say, 300 hours or so. And here we're seeing the effects of that, is the equipment can run longer before we have a downing event. Vice versa, maybe in the previous curve with the wear out, we implemented a change and it made things worse. Could be the phenomena that's occurring. If I was prioritizing these things, which one would you want to, we're at 1,000 hours operating these 3 machines, which one would you want to focus on? Well, hopefully that becomes obvious, because the number of failures I am going to expect with the simple extrapolation of this data is that machine 2 is going to have my next failure, followed by machine 1 on a rhythm, and machine 3 with its getting better and better. So maybe I don't want to change anything with this one. Keep it running just as is. So you can see how just a simple plot, not a terrible amount of math. There's no math. Essentially, it's just the plot and counting, and I can make comparisons, I can make decisions, I can ask better questions, I can focus on how do I make this thing work. So one way to quantify cumulative failures at times, so Sandra, I'm not exactly sure I understand. Just quantify, it's just a count. If I have downing events, or let's say I'm in a truck roll occurs, and I want to keep track of how many times I'm rolling a truck to a site or to a maintenance team out to a piece of equipment. then it's really just the count of how many times that occurs. Right. Now, one caveat in all of this is that the failure time is relatively small versus the operating time. So if you're in the order of 1 to 5% of your total time is in downtime, this will still work fairly well. Where it gets complicated is if you have a long downtime. Let's say that this failure here at 450 hours or so, let me see if I can get, took 200 hours to repair. Well, it slants the ability of my curve to tell this story, or skews it some. So what I've seen people do is they'll put a block here basically saying this was all downtime. And so the analysis and the way to appropriately do this gets more complicated when you have significant downtime. And there's a handful of tricks of accounting for that downtime and restarting the operating clock and adjusting the plot. But that's beyond the scope of what I wanted to talk about today. So another way, and your crew, TrueSanders, is that you can do a curve fit to these things. And I'll show you some examples of that in a couple examples coming up. Weibull++ has a renewal, a set of parametric and non-parametric curve fitting algorithms for doing mean cumulative function fitting. And those can tell a story too. One of the things that ReliaSoft put out in a paper some years ago was a means to determine if your maintenance program is helping or hurting your equipment. So to what extent, what proportion did your repair restore the equipment to good as new, or did it restore it to as bad as old? There's some fraction in between. And so we'll take a look at that in these examples. So cumulative plots, are they related to the Crow-AMSA plots? I think, and correct me if I'm wrong, the Crow-AMSA models uses log-log plots. And so they are related in that realm because we are looking at cumulative downing events or cumulative reported bugs or failures and over time, right? I know that some of those models also tend to look at, I'm going to do a week of evaluation, calculate MTBF, and then plot MTBF versus time, which I always thought was odd since why don't you just plot the data? But here's some actual data. I gathered this some years ago when I was working with a client, and I believe I've obscured it enough that you won't be able to recognize who it is. But here's that curve fit, Sander, is that they put I think this was a parametric curve, and it's given me beta eta, and there is a formula, which I don't recall at the moment. It's not, I don't believe it's Weibull, it's some variant of that. But here's this RF, it's called the restoration factor. Is this, so is it being restored to as good as new? And it's saying that it's only 20% as good as new. Or I'm sorry, as it's close to as good as new, but getting, you can see that it has a slight overall curve as concave and getting a bit worse, but it's also much more complicated than that. We have these clusters of events that occur in groups, and when I dug into the story some more, so John, the restoration factor is calculated by the Weibull++ software, and Adam, and I'm drawing a complete blank on his last name, wrote a really nice paper, and it's up on the Weibull.com site of look for restoration factor or for renewal data. It wasn't Adam Brett. Meta is Greek, and he's got a name like my last name, goes on forever, but it's Adam M. is what I always knew him as. But anyway, it talks about that the algorithm allows us to avoid making the assumption that the repair puts the machine as good as new. When we know that, like my car in high school, is that if I replace the fuel pump, it really had no effect on the age or the likelihood of failure of the water pump. And I'm sure there's some relationship at some point, but a new fuel pump doesn't help my water pump avoid failure. So the equipment was really as bad as old, except for one new piece in it. So it was closer to still old car. Where if I would have replaced everything under the hood and the entire drivetrain, it's closer to being as good as new, and the likelihood of failure would be lower. So that's what this restoration factor talks about, is that after each repair, how close to back to new is it? And it evaluates, in some regard, how good is your maintenance program in restoring equipment to as good as new. But I look at more details of just this graph. So here's a point from here, from about, what, 4,000 hours to up close to 8,000 hours. I'm increasing in failure rate, increasing in renewal, or the number of repairs that are occurring, right? And then maybe somebody did some major repairs at this spot, and it got better for a while, but then it started jumping straight up again. And so when I look at the data, I look at, well, what's this cluster of 4? Are they related? What's this cluster of 3? Are they related? And when we dug into it, is that this was equipment that was operation sensitive. There was immense pressure to get it running, get the production going. So the technician goes out, does a quick diagnosis, and restarts the equipment. If it runs, does safety checks and walks away. Doesn't actually fix anything. Well, a few hours later, it failed again. It just failed. Diagnostic is a quick check, restart it, it runs. So the third time, it happened quick enough that there was local memory of it occurring frequently. And so the maintenance manager says, hey, spend some time and solve that one. What's going on there? And so the technician spent a little bit more time, actually found a sensor that was out of alignment and fixed it. It took longer than 10 minutes. It took probably half an hour. But they actually got it running, and then they had failure-free operation for hundreds of hours. And what I saw in this particular situation was that each of these clusters were quick fixes, jerry-rig it, get it running, and then eventually somebody said, well, we got to really fix it. And so each of these patterns were a story in that regard. So as we looked at the details of the technician's notes and repair data that they gathered, the first couple of each of these patterns was restart, check for safety, restart, check for safety. Whereas the last one in these groups was found a dirty sensor, an alignment issue, a faulty bearing. There were things that would cause these intermittent failures, but weren't always obvious to a quick inspection. So let's take a look at another one. What do you see here? What questions would you ask? Yeah, I just seeing your note, Brian. Yeah, sometimes good things happen. I also, in this data set, I also spent more time looking at these gaps. Was that a long downtime? There was a number of pieces of equipment that would take the system down for 3, 4, 5,000 hours while they waited for spares or the right equipment to effect a repair. But if this was all fairly quick repairs, right away you can see there's some stories developing here. So what do you see happening here? What questions would you have? Yeah, those pairs of failures. Yeah, what's going on with that? Is the first one like the last one where it was just a quick check and then a second technician fixed it? Or was there a precursor failure occurring that basically forewarned us that something more major was going to occur or something else was going to occur? So if we see a pattern like that, these pairs, if it's a precursor, let's affect both repairs on the first trip. Let's change our maintenance practice that, if we see X occur on this equipment, go ahead and fix Y also because it's about to go. Yeah, it could be two different technicians. The first one didn't know exactly what they were looking for. The second one fixed it, and it stayed fixed for a while. But those are the types of questions that the simple dot pattern here is telling us what's going on. So let's try another one. Right? I tried to pick one that was actually getting better with time. Uh, so what do you see here? Yeah, stop messing with it. Yeah, exactly. But it still has these couplets, right? These little pairs. Similar pattern here, but it's also not going to be a high priority for us because it seems to be getting better. Now, if we ended up with a third point here and a fourth point here, yeah, then I'd focus on it some more. Yeah. And this one, depending on did we just install it or was it arbitrary that I started the timeline here? Uh, and our data only went back about a year in any meaningful way. But there was a startup kind of issue here. There was a series of things. They had just done a major overhaul on it, and there was a bunch of adjustments they had to do, and they captured some of the data. But then it seemed to settle in and behave fairly well over time. And so, and that's right, Sandra, the beta and eta here are not specifically Weibull plots. This is from the renewal data feature in, it's one of the special folios. Um, that's in Weibull++. And I think they use beta and eta because I think it's similar to Weibull, but it's a bit different formula because it accounts for this renewal factor. All right, I think I have one more. This one was a much more interesting piece of equipment. Yeah, so the renewal on this one is the repairs certainly did not bring it back to as good as new. It took it further away from good, so a high renewal factor number. But you can see these long strings of multiple calls to go address this piece of equipment, not the couplets that we were seeing before. So what might this suggest? This pattern of like 10 in a row, almost daily, looking at it. Yeah, you got the developers out of there, right? Yeah, always blame the designers. That's, yeah, yeah. Intermittent failure, that's what immediately comes to my mind is that it was a difficult failure to replicate and to find and to diagnose. It was something we weren't familiar with. So the technician would go out and check the logs and check the diagnostics and run some tests and really couldn't find what was causing the problem. And everything seemed to work fine for, 20, 30 hours, and then it's off and running and fails again. So some of our equipment is really tough to find problems, especially when it is intermittent. There is real pressure to get the machine running. And if it runs fine for 10 minutes, the operations manager is going to be looking over your shoulder saying, hey, walk away, let it run, let's run. And they've got pressures to get products out, right? And that just exists. Yeah, it would be nice if we saw this kind of pattern is go back to the operations manager saying, hey, what's the cost of unscheduled downtime? Let us sort this one out. Let us spend the time, spend an hour or two and troubleshoot this and solve it. And then we won't be back out here every day. Sometimes it takes building that trust that, hey, this is a problem, is a fluke, a one-time intermittent per year, or this is, once you have a pattern like this in your data set, you've already experienced it and you can build that case that, hey, we need to shut it down and fix this thing and solve it. Or you plan it for your next shutdown or turnaround, or you get it on the schedule to prioritize. Let's sort out what's happening here. But hopefully you can learn from what's happening so that if you see 2 or 3 of these in a row, it's a signal that's here's where you need to look a little deeper or you need to do more investigation. So yeah, and I agree, Brian. It also could be the operating conditions. It could be time of day. It could be different shifting. Look at this versus what else is going on in your plant, and put it in context. But the idea is that these patterns immediately focus us of where we need to start asking questions, where we need to dig deeper into our analysis. And if you've got a lot of equipment, generating simple plots like this is one way to start telling that story. So in those set of data plots I just showed, those samples, I had almost 200 pieces of equipment, 200 assets. And so we had some that were more exposed to the elements and some were more protected. And just running comparisons between those, plotting them next to each other, allowed us to see the value of having them sheltered and protected. So it made the argument to a financial argument to add sheltering equipment and enclosures for the exposed ones. And so we needed capital to do that, but we could justify it based on the cost of downtime and the cost of repairs. And it's a longer term fix than just going out and doing the repair, but we needed the data to make the justification. So it was one way for us to find that information. We also looked at changes in maintenance programs. We looked at prioritization, all of those things that helped us to figure out where do we need to best use our resources to make improvements. And so in your factory, in your plant, you've got data. You probably have more data than you can deal with. Well, using just either the dot plots or I recommend the cumulative plots is a great way to get started. And then as Sandra was talking about is fitting curves to that and looking at those renewal factors and similar kinds of information can give you another level of refinement or detail in your data plots. Okay, so I think I've got a couple reminders here. Let me pull up the opening slide here. There we go. And you can see the download the slides if you want, and there's a couple other links there and so on. So I wanted to get across two simple points. One, don't use MTBF. Hopefully that was clear. And two is just plot the data. A simple, very easy plot of the cumulative plot can help you see patterns that can focus your next steps of your investigation or of your improvement activities or whatever. It often goes a long way just to get a simple plot. And I like to say that even a manager can understand a cumulative plot. So I'll stay on the line. If there's any other questions or comments that you'd like to do, I'll take a look for that. And I'm going to go ahead and I'll keep the recording going here for a few minutes. You're welcome, Brian. Thanks for participating and asking questions and observations. Yeah, plotting goes a long way. It was the first thing I learned in school on data analysis classes was just plot it. Just plot it a couple different ways. So the reference for the RF calculation is go to Weibull.com or Reliasoft.com into their help files and manuals and stuff and look for renewal data analysis or repairable data analysis. And I believe RF stands for renewal function. And you should be able to find the formulas and the papers that were published on it. Well, everybody, you're welcome. I appreciate it. And thanks for joining. And Sanjeev, you're welcome. Thanks for being the first time. Hopefully it's not the last. I understand it. I think if I remember right, you're in Bangalore, so it might be not a great timeline. We do record these. I do record them. Most of the time I hit the record button. And they're available underneath reliability.fm as part of the Sendo Reliability webinar podcast series. So you can get an audio recording through iTunes and Stitcher. But if you're a member of the site and logged in, you can also get a video recording of the slides and the actual event. All right, so thanks, Long Chen. I see you, a few names, Gene, Ray, a handful of folks I've seen before. Kirk, you're a regular. Appreciate you joining again today. Yeah, Christopher, I was just having that discussion the other day, is if you recall the Nolan and Heap study, it was for aircraft of United Airlines in the 70s, I believe it was. And their maintenance program was pretty aggressive at replacing systems regularly. I mean, they didn't wait for wear outs because of the catastrophic nature of say, a braking system wearing out or an engine failure. So they were pretty aggressive at making failure replacements before wear out had a chance to occur. And that was by design of their maintenance program. So it's not surprising that there wasn't a huge number of wear out failures in their analysis because they just didn't wait for that to occur. So every industry and every set of equipment will have a different set of curves. The Nolan and Heap study provided curves and data breakout for that particular set of equipment. So your equipment, depending on your maintenance program and strategy, is very likely to have a completely different proportions of typical curves. So what I recommend is that you get started, collect the data, do the cumulative plots, and start looking at what's happening with your equipment. Now, as you dig deeper into the top hitters, the things you see that you're replacing more often, and the risk assessment work, and all the other pieces that go into a reliability-centered maintenance, you can start to focus on, well, do I have a wear-out mechanism that I need to prevent, or do I have equipment that actually could run longer? And let's do some experiments to see what its behavior is if we extend the maintenance periods and so on. So there's plenty of things you can do, but you got to start with the data, and don't rely on a study of Boeing aircraft maintenance practices in the 70s. I think that's something to be avoided. So hopefully that makes sense. All right. All right, good. I like it when that happens. I get lucky that way sometimes. All right, well, thanks everybody for joining. And I'll stay on the line. I'm going to go ahead and end the recording, but I'll stay on the line if there's